Whether you're new to Rust or a seasoned developer, Chapter 4 of the Rustbook is the pivotal chapter. Here's where we will discuss the most controversial topic in Rust development: ownership. I want to give a huge shout out to the members of the channel: Seth, Hamdi, Steven. You guys rock. Let's go.
Understanding ownership. Ownership is Rust's most unique feature and has deep implications for the rest of the language. It enables Rust to make memory safety guarantees without needing a garbage collector. So it's important to understand how ownership works. In this chapter, we'll talk about ownership as well as several related features: borrowing, slices, and how Rust lays data out in memory. Let's do it. What's ownership? Ownership is a set of rules that govern how a Rust program manages memory. All programs have to manage the way they use a computer's memory while running. Some languages have garbage collection that regularly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks. If any of the rules are violated, the program won't compile. None of the features of ownerships will slow down your program while it's running. Because ownership is a new concept for many programmers, it does take some time to get used to. The good news is that the more experienced you become with Rust and the rules of ownership system, the easier you will find it to naturally develop code that is safe and efficient. Keep at it. When you understand ownership, you will have a solid foundation for understanding the features that make Rust unique. In this chapter, you'll learn ownership by working through some examples that focus on a very common data structure: strings, the stack and the heap. Many programming languages don't require you to think about the stack and the heap very often. But in a systems programming language like Rust, whether a value is on the stack or the heap affects how the language behaves and why you have to make certain decisions. Parts of ownership will be described in relation to the stack and the heap later in this chapter, so here is a brief explanation in preparation. Both the stack and the heap are parts of memory available to your code to use at runtime, but they are structured in different ways. The stack stores values in the order it gets them and removes the values in the opposite order. This is referred to as last in, first out. Think of a stack of plates. When you add more plates, you put them on top of the pile, and when you need a plate, you take one off the top. Adding or removing plates from the middle or bottom wouldn't work as well. Adding data is called pushing onto the stack, and removing data is called popping off the stack. All data stored on the stack must have a known fixed size. Data with an unknown size at compile time or a size that might change must be stored on the heap instead. The heap is less organized. When you put data on the heap, you request a certain amount of space. The memory allocator finds an empty spot in the heap that is big enough, marks it as being in use, and returns a pointer, which is the address of that location. This process is called allocating on the heap and is sometimes abbreviated as just allocating. Pushing values onto the stack is not considered allocating. Because the pointer to the heap is a known fixed size, you can store the pointer on the stack. But when you want the actual data, you must follow the pointer. Think of being seated at a restaurant. When you enter, you state the number of people in your group, and the host finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you have been seated to find you. Pushing to the stack is faster than allocating on the heap because the allocator never has to search for a place to store new data. That location is always at the top of the stack. Comparatively, allocating space on the heap requires more work because the allocator must first find a big enough space to hold the data and then perform bookkeeping to prepare for the next allocation. Accessing data in the heap is slower than accessing data on the stack because you have to follow a pointer to get there. Contemporary processors are faster if they jump around less in memory. Continuing the analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all the orders at one table before moving on to the next table. Taking an order from table A, then an order from table B, then one from A again, and then one from B again will be a much slower process. By the same token, a processor can do its job better if it works on data that's close to other data, as it is on the stack, rather than further away, as it can be on the heap. When your code calls a function, the values passed into the function, including potentially pointers to the data on the heap, and the function's local variables get pushed onto the stack. When the function is over, those values get popped off the stack. Keeping track of what parts of the code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. Once you understand ownership, you won't need to think about the stack and the heap very often, but knowing that the main purpose of ownership is to manage heap data can help explain why it works the way it does. Ownership rules. First, let's take a look at the ownership rules. Keep these rules in mind as we work through the examples that illustrate them. Each value in Rust has an owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. Variable scope. Now that we are past the basic Rust syntax, we want to include all the function main code in examples. So if you are following along, make sure to put the following examples inside a main function manually. As a result, our examples will be a bit more concise, letting us focus on the actual details rather than the boilerplate code. I love that. As a first example of ownership, we'll look at the scope of some variables. A scope is a range within a program for which an item is valid. Take the following variable. Let s equals to hello. The variable s refers to a string literal, where the value of the string is hard-coded into the text of our program. The variable is valid from the point at which it's declared until the end of the current scope. Listing for 1 shows a program with comments annotating where the variable s will be valid. Okay, so here is not valid, so this is before the declaration. Here, s is valid from this point forward. Then you do some stuff with s, and then when the scope is over, s is no longer valid. In other words, there are two important points in time here. When s comes into scope, it is valid. It remains valid until it goes out of scope. At this point, the relationship between scopes and when variables are valid is similar to that in other programming languages. Now, we'll build on top of this understanding by introducing the string type. The string type. To illustrate the rules of ownership, we need a data type that is more complex than those we covered in data types sections of chapter 3. The types covered previously are of a known size, can be stored on the stack and popped off the stack when their scope is over, and can be quickly and trivially copied to make a new, independent instance if another part of the code needs to use the same value in a different scope. But we want to look at data that is stored on the heap and explore how Rust knows when to clean up that data. And the string type is a great example. We'll concentrate on the parts of string that relate to ownership. This aspect also applies to other complex data types, whether they are provided by the standard library or created by you. We'll discuss string in more depth in chapter 8. We have already seen literals, where a string value is hard-coded into our program. String literals are convenient, but they aren't suitable for every situation in which we may want to use text. One reason is that they are immutable. Another is that not every string value can be known when we write our code. For example, what if we want to take user input and store it? For these situations, Rust has a second string type, string. This type manages data allocated on the heap and as such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using the from function, like so. The double colon operator allows us to namespace this particular from function under the string type, rather than using some sort of name like string from. We'll discuss this syntax more in the method syntax section of chapter 5. And when we talk about namespacing with modules in paths for referring to an item in the module tree in chapter 7. This kind of string can be mutated. So we declare it as a mutable string. Then we push a literal to string, and then we just print it. So what's the difference here? Why can literal be mutated but literals cannot? The difference is in how these two types deal with memory. Memory and allocation. In the case of a string literal, we know the contents at compile time, so the text is hard-coded directly into the final executable. This is why string literals are fast and efficient, but these properties only come from the string literal's immutability. Unfortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time and whose size might change while running the program. With the string type, in order to support a mutable, grabbable piece of text, we need to allocate an amount of memory on the heap. unknown at compile time, to hold the contents. This means the memory must be requested from memory allocator at runtime. We need a way of returning this memory to the allocator when we are done with our string. That first part is done by us. When we call string : from, its implementation requests the memory it needs. This is pretty much universal in programming languages. However, the second part is different. In languages with a garbage collector, the GC keeps track of and cleans up memory that isn't being used anymore, and we don't need to think about it. In most languages without a GC, it's our responsibility to identify when memory is no longer being used and to call code to explicitly free it, just as we did to request it. Doing this correctly has historically been a difficult programming problem. If we forget, we'll waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, that's a bug too. We need to pair exactly one allocate with exactly one free. Think about when Apple introduced ARC, or automatic reference counting, to Objective-C. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our scope example from listing 4.1 using string instead of a literal. Cool. There's a natural point at which we can return the memory our string needs to the allocator, when s goes out of scope. When a variable goes out of scope, Rust calls a special function for us. This function is called dropped, and it's where the author of string can put the code to return the memory. Rust calls drops automatically at the closing curly bracket. Note, in C++, this pattern of deallocating resources at the end of an item's lifetime is sometimes called resource acquisition is initialization. The drop function in Rust will be familiar to you if you have used RAII patterns. This pattern has a profound impact on the way Rust code is written. It may seem simple right now, but the behavior of code can be unexpected in more complicated situations when we want to have multiple variables use the data we have allocated on the heap. Let's explore some of those situations now. Variables and data interacting with move. Multiple variables can interact with the same data in different ways in Rust. Let's look at an example using an integer in listing 4.2. We can probably guess what this is doing. Bind the value to 5 to x, then make a copy of the value in x and bind it to y. We now have two variables, x and y, and both equal 5. This is indeed what is happening, because integers are simple values with a known fixed size, and these two 5 values are pushed onto the stack. Now let's look at the string version. All right. This looks very similar, so we might assume that the way it works will be the same. That is, the second line will make a copy of the value in S1 and bind it to S2. But this isn't quite what happens. Take a look at figure 4.1 to see what's happening to string under the covers. A string is made of 3 parts, shown on the left. A pointer to the memory that holds the contents of the string, a length, and a capacity. This group of data is stored onto the stack. On the right is the memory on the heap that holds the contents. All right, so pointer, length, and capacity. The length is how much memory in bytes the contents of the string are currently using. The capacity is the total amount of memory in bytes that the string has received from the allocator. The difference between the length and capacity matters, but not in this context. So for now, it's fine to ignore the capacity. When we assign S1 to S2, the string data is copied, meaning that we copy the pointer, the length, and capacity that are on the stack. We do not copy the data on the heap that the pointer refers to. In other words, the data representation in memory looks like figure 4.2. So here we have S1 and S2. They both have pointers to the same element in the heap. The representation does not look like 4.3, which is what memory will look like if Rust instead copied the heap data as well. If Rust did this, the operation S2 equals to S1 will be very expensive in terms of runtime performance if the data on the heap were large. All right. So here what we're saying is that this is not how Rust works, where S1 allocates its own data on the heap. Earlier we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for that variable. But figure 4.2 shows both data pointers pointing to the same location. And this is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. This is known as a double free error and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety, after the line let S2 equals to S1, Rust considers S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It just won't work. You'll get an error like this because Rust prevents you from using the invalidated reference. So we see that we are trying to use S1, and then we get mover error borrow of moved value. If you have heard the terms shallow copy and deep copy while working with other languages, the concept of copying the pointer, length, and capacity without copying the data probably sounds like making a shallow copy. But because Rust also invalidates the first variable, instead of being called a shallow copy, it is known as a move. Very careful, guys. That's a unique Rust concept. In this example, we will say that S1 was moved into S2. So what actually happens is shown in figure 4.4. Representation in memory after S1 has been invalidated. So it's like what, grayed out. That solves our problem. With only S2 valid, when it goes out of scope, it alone will free the memory. And we are done. In addition, there's a design choice that is implied by this. Rust will never automatically create deep copies in your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. Variables and data interacting with clone. If we do want to deeply copy the heap data of the string, not just the stack data, we can use a common method called clone. We'll discuss method syntax in chapter 5, but because methods are a common feature in many programming languages, you have probably seen them before. Here's an example of the clone method in action. All right, so we are cloning, recreate S1, and then we clone S1 into S2. This works just fine and explicitly produces the behavior shown in figure 4.3, where the heap data does get copied. And let's go back to it so that we are on the same page here. Now we indeed are allocating two strings on the heap that are independent between them. When you see a call to clone, you know that some arbitrary code is being executed and that code may be expensive. It's a visual indicator that something different is going on. Stack only data copy. There's another wrinkle we haven't talked about yet. This code using integers, part of which was shown in listing for 2, works and is valid. So here we don't run into the scenario where X just becomes invalid. But this code seems to contradict what we just learned. We don't have to call to clone, but X is still valid and wasn't moved into Y. The reason is that types such as integers that have known size at compile time are stored entirely onto the stack. So copies of the actual values are quick to make. That means that there's no reason we will want to prevent X from being valid after we create the variable Y. In other words, there's no difference between deep and shallow copying here. So calling clone wouldn't do anything different from the usual shallow copying, and we can leave it out. Rust has a special notation called the copy trait that we can place on types that are stored on the stack, as integers are. And we'll talk more about this in chapter 10. If a variable implements the copy trait, variables that use it do not move, but rather are trivially copied, making them still valid after assignment to another variable. Rust won't let us annotate with copy if the type or any of its parts has implemented the drop trait. If the type needs something special to happen when the value goes out of scope and we add the copy annotation to that type, we'll get a compile time error. To learn about how to add the copy annotation to your type to implement the trait, see derivable traits in Appendix C. So what types implement the copy trait? You can check the documentation for the given type to be sure, but as a general rule, any group of a simple scalar values can implement copy, and nothing that requires allocation or some form of resource can implement copy. Here are some of the types that implement copy. All integer types such as U32, the Boolean type, bool with values true and false. All the floating point types such as F64, the character type, tuples, if they only contain types that also implement copy. So for example, I32 and I32, so a tuple of I32, I32 implements copy, but A tuple of i32 and string does not, because string cannot implement copy. Ownership and functions. The mechanics of passing a value to a function are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy, just as assignment does. Listing for 3 has an example with some annotations showing where variables go into and out of scope. All right. So here, S comes into scope. Then this function takes ownership of S. So S is no longer valid here. Then X comes into scope. Then X will move into the function, but i32 is copy, so it's okay to still use it So it's okay to still use X afterward, because it will just make a copy and pass it to the function here. Here, X goes out of scope, then S. But because S value was moved, nothing special happens. Here we see that takes ownership will take the ownership of S and just print it. Makes copy, it just prints it as well. If we try to use S after the call to takes ownership, Rust will throw a compile time error. These static checks protect us from mistakes. Try adding code to main that uses S and X to see where you can use them and where the ownership rules prevent you from doing so. Return value and scope. Returning values can also transfer ownership. Listing for 4 shows an example of a function that returns some value, with similar annotations as those in listing for 3. So S1 gives ownership. Gives ownership moves its return value into S1. I see. So gives ownership returns a string. Gives ownership will move its return value into the function that calls it. So we allocate a string here, and then we just return it, and that's that. And then takes S2, takes ownership of S2, and then gives it back to S3. Cool. A string is returned and moves out of the calling function. Cool. The ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes data on the heap goes out of scope, the value will be cleaned up by drop unless ownership of the data has been moved to another variable. While this works, taking ownership and then returning ownership with every function is a bit tedious. What if we want to let a function use the value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we want to use it again, in addition to any data resulting from the body of the function that we might want to return as well. Rust does let us return multiple values using a tuple, as shown in listing for 5. So calculate length will return an integer, usize. It will return a usize and a string, which is cool. But this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for using a value without transferring ownership, called references. Guys, this one is like a big deal, so let's do this together. References and borrowing. The issue with the tuple code in listing 4.5 is that we have to return the string to the calling function so we can still use the string after the call to calculate length, because the string was moved into calculate length. Whoa, someone is hungry. Instead, we can provide a reference to the string value. A reference is like a pointer in that it's an address we can follow to access the data stored at that address. That data is owned by some other variable. Unlike a pointer, a reference is guaranteed to point to a valid value of a particular type for the life of that reference. Here is how you will define and use a calculate function that has a reference to an object as a parameter instead of taking ownership of the value. All right. Fair enough. Here's how we declare that a parameter. It's great. First, notice that all the tuple code in the variable declaration and the function return value is gone. Second, note that we pass ~s1 into calculate length, and in its definition, we take ampersand string rather than string. These ampersands represent references, and they allow you to refer to some value without taking ownership of it. Figure 4.5 depicts this concept. All right, so here we have the reference S that references S1. Note, The opposite of referencing by using ampersand is dereferencing, which is accomplished with the dereference operator star. We'll see some uses of the dereference operator in chapter 8 and discuss details of the dereferencing in chapter 15. Let's take a closer look at the function call here. All right, let's take a closer look then. The ampersand S1 syntax lets us create a reference that refers to the value of S1 but does not own it. Because it does not own it, the value it points to will not be dropped when the reference stops being used. Likewise, the signature of the function uses ampersand to indicate that the type of the parameter S is a reference. Let's add some explanatory annotations. All right, let's do it. So here S is a reference to a string. And then here S goes out of scope, but because it does not have ownership of what it refers to, it is not dropped. Check. The scope in which the variable S is valid is the same as any function parameter's scope. But the value pointed to by the reference is not dropped when S stops being used, because S doesn't have ownership. When functions have references as parameters instead of the actual values, we won't need to return the values in order to give back ownership, because we never had ownership. We can call the action of creating a reference borrowing. As in real life, if a person owns something, you can borrow it from them. When you're done, you have to give it back. You don't own it. So what happens if we try to modify something we are borrowing? Try the code in listing 4.6. Spoiler alert, it doesn't work. All right, so let's try pasting it here. Sure enough, we cannot borrow star SomeString as mutable, as it is behind an ampersand reference. SomeString is an ampersand reference, so the data it refers to cannot be borrowed as mutable. Consider changing this to be a mutable reference. All right, cool. Just as variables are immutable by default, so are references. We are not allowed to modify something we have a reference to. Mutable references. We can fix the code from listing 4.6 to allow us to modify a borrowed value with just a few small tweaks that use instead mutable references. So we have a mutable. We are declaring this as mutable. And then we declare this as mutable as well. And this is mutable as well. First, we change S to be mute. Then we create a mutable reference with ampersand mute S, where we call the change function and update the function signature to accept a mutable reference with SomeString : ampersand mute string. This makes it very clear that the change function will mutate the value it borrows. Mutable references have one big restriction. If you have a mutable reference to a value, you can have no other references to that value. This code that attempts to create two mutable references to S will fail. Makes sense. I believe in you. I don't need to run every single. Here's the error. First mutable borrow occurs here, and then there's a second mutable borrow. This error says that this code is invalid because we cannot borrow S as mutable more than once at a time. The first mutable borrow is in R1 and must last until it's used in the print line. But between the creation of that mutable reference and its usage, we try to create another mutable reference in R2 that borrows the same data than R1. The restriction preventing multiple mutable references to the same data at the same time allows for mutation, but in a very controlled fashion. It's something that new Rustaceans struggle with because most languages let you mutate whatever you like. The benefit of having this restriction is that Rust can prevent data races at compile time. Guys, that's huge. A data race is similar to a race condition and happens when these three behaviors occur. Two or more pointers access the same data at the same time. At least one of the pointers is being used to write to the data. There's no mechanism being used to synchronize access to the data. Data races cause undefined behavior and can be difficult to diagnose and fix when you are trying to track them down at runtime. Rust prevents this problem by refusing to compile code with data races. That's easier. As always, we can use curly braces to create a new scope, allowing for multiple mutable references, just not simultaneous ones. Okay, so this is the first borrow. And because it goes out of scope, then you can do a second borrow, which is perfectly fine. Rust enforces a similar rule for combining mutable and immutable references. This code results in an error. Let's see. So here's the first immutable reference, second immutable reference, and then we are borrowing mutably here. Here's the error. So we have a mutable borrow. Phew, we also cannot have a mutable reference while we have an immutable one to the same value. Users of an immutable reference don't expect the value to suddenly change out from under them. However, multiple immutable references are allowed because no one who is just reading the data has the ability to affect anyone else's reading of the data. Note that a reference's scope starts from where it is introduced and it continues throughout the last time that a reference is used. For instance, this code will compile because the last usage of the immutable references, the print line, occurs before the mutable reference is introduced. Okay, let's see if we can grok this. So here we do two immutable borrows. Variables are R1 and R2 will not be used after this point. And then we do a mutable, borrowing of S. But because R1 and R2 are no longer used, then the compiler is smart enough to figure out that this is not a problem. The scopes of the immutable references R1 and R2 end after print line, where they are last used, which is before the mutable reference R3 is created. These scopes don't overlap, so this code is allowed. The compiler can tell that the reference is no longer being used at a point before the end of the scope. Even though borrowing errors may be frustrating at times, remember that it's the Rust compiler pointing out a potential bug early, at compile time rather than at runtime, and showing you exactly where the problem is. Then you don't need to track down why your data isn't what you thought it was. How awesome is that, guys? This is just fantastic. Dangling references. In languages with pointers, it's easy to erroneously create a dangling pointer, which is a pointer that references a location in memory that may have been given to someone else, by freeing some memory while preserving a pointer to that memory. In Rust, by contrast, by design, the compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. Let's try to create a dangling reference to see how Rust prevents them with a compile time error. Okay, so here we're trying to return this reference to S, but S will be deallocated. So this shouldn't compile. And here's the error. Whoa, okay. So the bottom line is we cannot return a reference to local variable S. Ampersand S returns a reference to data owned by the current function. This error message refers to a feature we haven't covered yet, lifetimes. We'll discuss lifetimes in detail in chapter 10, but if you disregard the parts about lifetimes, the message does contain the key to why this code is a problem. This function's return type contains a borrowed value, but there is no value for it to be borrowed from. Fair enough. Let's take a closer look at exactly what's happening at each stage of our dangle code. And this is super important, guys. So the dangle occurs, dangle returns a reference to a string. Okay, so that's right here. S is a new string. Then ampersand S, we return a reference to the string S. Here, S goes out of scope. S goes out of scope and it's dropped. Its memory goes away. Danger. It shouldn't compile. Because S is created inside dangle, when the code of dangle is finished, S will be deallocated. But we try to return a reference to it. That means this reference will be pointing to an invalid string. That's just not good. Rust won't let us do this. The solution here is to return the string directly. So you'll return it and you'll give ownership to the caller, which is great. This works without any problems. Ownership is moved out and nothing is deallocated. The rules of references. Let's recap what we have discussed about references. At any given time, you can have either one mutable reference or any number of immutable references. References must always be valid. Next, we'll look at a different kind of reference, slice. the slice type. Slices let you reference a contiguous sequence of elements in a collection rather than the whole collection. A slice is kind of a reference, so it does not have ownership. Okay. Here's a small programming problem. Write a function that takes a string of words separated by spaces and returns the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word, so the entire string should be returned. Let's work through how we will write the signature of this function without using slices to understand the problem that slices will solve. So here we're saying, okay, the function signature, the first word function has an ampersand string as a parameter. We don't want ownership, so this is fine. But what should we return? We don't really have a way to talk about parts of a string. However, we could return the index of the end of the word, indicated by a space. Let's try that. Okay, so we return a usize where usize is the index. Okay, let's do it. So what we do is we transform s to bytes, and then we iterate through the bytes, and we use enumerate so that we get index and value. And then we say, well, if item or value equals to a space, you found the index of the first word. Else, just return the length of the whole string. Because we need to go through the string element by element and check whether a value is a space, we'll convert our string to an array of bytes using the asBytes methods. Cool. Next, we create an iterator over the array of bytes using the iter method. We'll discuss iterators in more detail in chapter 13. For now, know that iter is a method that returns each element in a collection, and that enumerate wraps the result of an iter and returns each element as part of a tuple instead. The first element of the tuple returned from enumerate is the index, and the second element is a reference to the element. This is a bit more convenient than calculating the index ourselves. Because the enumerate method returns a tuple, we can use patterns to destructure that tuple. We'll be discussing patterns more in chapter 6. In the for loop, we specify a pattern that has I for the index in the tuple and ampersand item for the single byte in the tuple. Because we get a reference to the element from .iter.enumerate, we use ampersand in the pattern. Inside the for loop, we search for the byte that represents the space by using the byte literal syntax. If we find a space, we return the position. Otherwise, we return the length of the string by using s.len. We now have a way to find out the index of the end of the first word in the string. But there's a problem. We are returning a usize on its own, but it's only a meaningful number in the context of the ampersand string. In other words, because it's a separate value from the string, there's no guarantee that it will still be valid in the future. Consider the program in listing 4.8 that uses the first word function from listing 4.7. Okay, so we create a string, hello world, compute the index of the first word, and then we empty the string, making it equal to just empty. Word still has the value 5 here. There is no more string that could meaningfully use the value 5 with. Word is now totally invalid. Cool. This program compiles without any errors and will also do so if we use word after calling s.clear. Because word isn't connected to the state of s at all, word still contains the value 5. We could use that value 5 with the variable s to try to extract the first word out, but this will be a bug because the contents of s have changed since we save 5 into word. Having to worry about the index in Word getting out of sync with the data in S is tedious and error-prone. Managing these indices is even more brittle if we write a second word function. Its signature will have to look like this. All right, that's annoying. Now we are tracking a starting and ending index, and we have even more values that were calculated from data in particular state, but aren't tied to that state at all. We have 3 unrelated variables floating around that need to be kept in sync. Luckily, Rust has a solution for this problem: string slices. String slices. A string slice is a reference to part of a string, and it looks like this. So here we create a string, and then we say ampersand s, and then what the range of the string that we are referencing to. So rather than a reference to the entire string, hello is a reference to a portion of the string, specified in the extra square bracket 0 to 5 bit. We create slices using a range within brackets by specifying starting index, ending index, where starting index is the first position in the slice and ending index is one more than the last position in the slice. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to ending index minus starting index. So in the case of let word equal to ampersand 6 is square bracket 6 to 11, word will be a slice that contains a pointer to the byte at index 6 of s with a length value of 5. All right, and here we are translating the range into the slice into a pointer. Okay, so s is just a pointer. No, okay, that's the string. And then word is the slice, and it points to index 6 with a length of 5. Well, that's great. With Rust's range syntax, if you want to start at index 0, you can drop the value before the two periods. In other words, these are equal. Okay. By the same token, if your slice includes the last byte of the string, you can drop the trailing number. That means these are equal. Fantastic. You can also drop both values to take a slice of the entire string. So these are equal. So doing a slice from 0 to length and just doing ... Note, string slice range indices must occur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. For the purposes of introducing string slices, we are assuming ASCII only in this section. A more throughout discussion of UTF handling is in the storing UTF encoded text with strings section of chapter 8. Okay. With all this information in mind, let's rewrite first word to return a slice. The type that signifies string slice is written as ampersand stir. All right, so we are going to return an ampersand stir. Okay, this is pretty cool. So it's the same code that we looked at before. The only difference is that instead of returning a U size, you return ampersand s square bracket 0 to I. That's clever. We get the index for the end of the word the same way we did in listing for 7, by looking for the first occurrence of a space. When we find a space, we return a string slice using the start of the string and the index of the space as the starting and ending indices. Now, when we call first word, we get back a single value that is tied to the underlying data. The value is made up of a reference to the starting point of the slice and the number of elements in the slice. Returning a slice also works for a second word function. We now have a straightforward API that's much harder to mess up because the compiler will ensure the references into the string will remain valid. Remember the bug in the program in listing for 8 when we got the index to the end of the string Remember the bug in the program in listing for 8 when we got the index to the end of the first word, but then we cleared the string so our index Remember the bug in the program in listing for 8 when we got the index to the end of the first word, but then cleared the string so our index was invalid? That code was logically incorrect, but didn't show any immediate errors. The problems will show up later if we kept trying to use the first word index with an empty string. Slices make this bug impossible, and let us know we have a problem with our code much sooner. Using the slice version of first word will throw a compile time error. So after clear, the references are invalid, I assume. Here's the compiler error. So we cannot borrow s as mutable because it's also borrowed as immutable. All right. So this is a mutable, this is a reference, and this is mutable. Let's see. So this is an immutable borrow, and this is a mutable borrow. Recall from the borrowing rules that if we have an immutable reference to something, we cannot also take a mutable reference, because clear needs to truncate the string. It needs to get a mutable reference. The print line after the call to clear uses the reference in Word, so the immutable reference must still be active at that point. Rust disallows the mutable reference in clear and the immutable reference in Word from existing at the same time, and compilation fails. Not only Rust made our API easier to use, but it has also eliminated an entire class of errors at compile time. Word. No pun intended. String literals as slices. Recall that we talk about string literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. Okay. The type of S here is &stir. It's a slice pointing to that specific point of the binary. This is also why string literals are immutable. &stir is an immutable reference. String slices as parameters. Knowing that you can take slices of literals and string values lead us to one more improvement on first word, and that's it. And that's its signature. A more experienced Rustation will write the signature shown in listing for 9 instead, because it allows us to use the same function on both string and stir values. If we have a string slice, we can pass that directly. If we have a string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of deref coercions, a feature we will cover in the implicit deref coercions with functions and methods section of chapter 15. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. Okay, so here we have a variation of the same program, but here first word, where's first word defined? Well, first word just takes an ampersand string or a ampersand stir as opposed to an ampersand string. That's what they are getting at. So it works on slices of string, whether partial or whole. First word also works on references to strings, which are equivalent to whole slices of strings. First word works on slices of string literals, whether partial or whole. Because string literals are string slices already, this works too, without the slice syntax. Other slices. String slices, as you might imagine, are specific to strings. But there's a more general slice type too. Consider this array. Just as we might want to refer to part of the string, we might want to refer to part of an array. We will do so like this. This slice has type &i32. It works the same way as string slices do, by storing a reference to the first element and a length. You'll use this kind of slice for all sorts of other collections. We'll discuss these collections in detail when we talk about vectors in chapter 8. Summary. The concept of ownership, borrowing, and slices ensure memory safety in Rust programs at compile time. The Rust language gives you control over your memory usage in the same way as other systems programming languages. But having the owner of data automatically clean up that data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Ownership affects how lots of other parts of Rust work. So we'll talk about these concepts further throughout the rest of the book. Let's move on to chapter 5 and look at grouping pieces of data together in a struct.